Alright, draft physics video and such. It's interrupted before, so yes, fell off the horse and now I've got to climb back on. Do have extra light now. Doesn't really fix anything, so that's doesn't make it that much better, realistically. But anyway, alright, so John the fucking Wayne made a video. And same kind of stuff. I mean, it's a half an hour video to explain what he claims to be very simple high school mathematics. Well, obviously it's not that simple. And, so it's on this interferometer subject, but it's most specifically on the idea of just when a frame is moving, does it change the length of time, the overall interaction takes place while it's moving. If the interaction's happening in the same direction as the movement, does the interaction take longer, or is it slower or faster? And I argue that no, it takes exactly the same amount of time. It's just that the proportion of time that happens going one way versus going the other way changes. The proportions change, but the absolute amount of time and the absolute amount of activity will be exactly the same. So I've tried to analogize this to different things. So one analogy I've used is two people talking on a train, and they're opposite each other, facing each other across a table. So their distance from each other is fixed. And I would argue that if they're having a conversation, in the direction of the motion, say the train's going 100 miles an hour, the words the person speaks will take longer to get received by the other person's ears. But the extra length, the extra amount of time, will be exactly the same as the amount of time shortened when the guy facing the person talks back, because what he says, you'll consume the distance by moving towards him, technically towards the words he speaks, not him, but towards the words he speaks. And you'll consume the distance between you and those words, and therefore it'll take less time, and it'll be exactly the same. Now, I thought of another way of analogizing it is if you have a dog, right, to point A and point B. So let's attempt a drawing, and then we'll play some of the whatever the saddle sword butt heads video. So you have a point A and a point B. Okay, and let's say I'm at point A and a dog is at point B, and neither and the dog's not going to move, and so we're just going to measure how long it takes for me to get to point B, and that would be the experiment. That would be the standard. And so the alternative things that can happen is I'm at point A, the dog's at point B, and the dog moves away from me. So now I have to go this extra distance to get to the dog. This will be point B. So point B moves to a new location. And the other example would be I'm at point A, it's always point A, the dog is moving towards me instead of away from me. And so now the amount of time I have to run is going to be shortened because the dog is going to consume. I should have did it in red, sorry. Kept it consistent. So forget it. And so the argument I would make is that the actual physics is that if you take these two circumstances and you add them together, okay, they'll equal this. You can divide them by 2. So if you take these two events, the dog running away from me and me catching it, the dog running towards me. You do those two experiments, time them, divide it by 2, you'll get exactly the same time as this took. And it's the same for the conversation on the train. So just imagine if, let's say I'm on the train and there's somebody sitting in the same booth that's the same distance as the length of the table. So I'm 3 feet away from them and I'm 3 feet away from the guy across the table. And I'm having a conversation. The conversation, let's say they're both going to respond. I'm going to say hello, and they're both going to say hello back. Both conversations will take exactly the same amount of time. Even though the conversation across the table is going to be different in the sense that one part of the conversation is going to be slower and one part is going to happen quicker. And this one side to side isn't going to be changed at all because there's not going to be any compression of the sound. There's not going to be any retardation or any acceleration in any of the conversation. And those two will be exactly the same. And that's the argument with the interferometer. They say it's different. They say this isn't true. That if I do these two experiments, it won't equal this distance. It'll equal some other distance. So so when they're doing the math, they're trying to claim that essentially that this distance and this distance are the same, and they're not. They're exactly opposite proportions, and they're kind of claiming that they can combine these two as if they're in the same circumstance, when in the one circumstance the line leaving point A in both cases is consuming distance. The point B thing in one case is expanding the distance and in the other case is contracting the distance. So it can't be compared. There's no symmetry between these two. So you have to consider them as a whole. But you can't do math across them and say there's a consistent time or there's a consistent distance. The distance is length is changing. There's no consistent length here. In one circumstance the length is contracting. In the other circumstance, the length is expanding. So there's no common variable. So you can't apply a mathematical formula where you establish that there is some constant here when there isn't. The only thing constant is both of the velocities, but nothing else is constant. None of the distances are constant. So when the dog's running towards me, the dog will get to me with, running fewer steps. And when the dog's running away, he'll do more steps. And the same will happen to me in the sense that I'll move less steps when we're moving towards each other, and I'll move more steps when we're moving in the same direction. So you can see the obvious asymmetry. When we're moving the same direction, is not the same as when we're moving towards each other. One's contracting the L and the other is expanding the L. Alright, so I'll do his math. I think that should be enough. I mean, those two analogies should be enough for you to understand this and understand that this is correct. That these two experiments are exactly 180 degrees difference, and if you combine them and divide by 2, they will give you the exact distance if neither point A or point B was moving. Understand, point B is moving in the experiment. They have to account for that in the math. Alright, so that really should be enough. Now let's go to the video. Very funny video, actually. I mean, it's like I said, it takes a half an hour and he keeps claiming how the math is so simple, an idiot could do it. Apparently we gotta go find an idiot. Anyway. So it starts off a little preachy. Where's the sound? I don't hear anything. Should be sound here. Have it all the way up. Sound. Hello, sound. Oh, maybe they didn't have any yet. Maybe that'll kick in. I don't remember. It's certainly not past him to make a video with no sound.
Real physicists use dry erase markers, not Sharpies.
Alright. Whatever. Yeah.
Why is that?
So the funny thing is he's doing this video and the camera's moving all over the place. So I'd argue that real physicists put their camera on a tripod when they're just do stuff on a whiteboard. So I mean, it's just this idiotic crap of these pointless and useless critiques of nonsense. So anyway, we'll move ahead and try to get to something like an actual argument, which might be somewhere around 3 minutes. Might be.
Is traveling this distance. Now, at t0, the mirror would be here, right? But the whole thing is moving. So, at t1...
The important thing is it's moving in the direction that the light is traveling. So it's not that it's just moving, it's taking point B and moving it further away. So obviously it has to take more time to go the first distance, because the first distance is going to be expanding, where the distance on the return trip will be contracting. It's a fundamental difference, a kind of obvious difference, and you can't just call it L for length and say the two are the same. One L is expanding, one L is contracting.
Everything will have moved. So this distance here that the light has traveled is actually, well,
after the expansion, that's the distance it travels. Before the expansion is the L you're using. You're using the before the expansion L, and it's the after expansion L is a completely different L.
We can see that's the, so first we assume this is length L. Okay.
So there, he just did it, see? We assume this is length L. L is an expanding length. Yes, it starts that way, but when it's contracting, L is going to get really small, and when it's expanding, L is going to get much larger. So there is no constant L in this scenario. It's not in here. There's only too much and too little. There's no just right. You can't have L, the just right variable, in a circumstance where neither leg is doing just right. One leg's doing expansion, one leg's doing contraction. There is no L just right.
So
or
it
L
will have
average.
traveled L plus V times T1. Right.
So velocity is already a timed derivative. So you can't multiply it times T1 because velocity is already distance over time. Yeah, time over distance, same difference. I mean, it's like frequency and wavelength, same thing, just inverted. Anyway, so the time is going to be the byproduct of the expansion and the contraction. The expansion and the contraction are the variables, and they're the things changing, and you don't have them in the equation. You have no expansion and contraction in the equation. The velocity is expanding the distance, not only for the thing moving, so to speak, but for the light. They're both happening concurrently. They're not additive. They're happening at the same time. They're both being obligated to travel farther to finish the experiment, because now point B is moving away from the light.
I mean, maybe people aren't aware of this, but velocity here is distance divided by time, units of time. So when you multiply it by the number of time units, you get back the distance that's traveled.
Yeah, so you're just complicating the equation. This isn't a velocity equation, it's a distance equation, and L is your distance. So see, you can't do distance plus distance. Well, technically you can. You could have just said distance plus distance. What's the extra distance that will have to be traveled? Okay, so you just do the standard distance, the distance at t1, and then do the distance at t2, and subtract the two, and you'll find that little bit of extra that was traveled at the slower velocity. But I'm just saying it's the distance. This is a distance equation, and you keep wanting to make it a timed equation. All right, let's move ahead to somewhere around
So
13, I think.
If you were traveling in a car 60 miles per hour and you were in the car for an hour, you will have traveled 60 miles.
Yeah, so he's doing the obvious, but it's no real point in pointing out how that has nothing to do with the fact that you're using L for distance, and L isn't a constant. It's expanding in one circumstance and contracting in the other throughout the entire event.
So T1 equals L C minus V, and if you did a similar thing, you would see T2 equals L C plus V. Okay, I'm not going to go through it.
Yeah, well, there's no point. Remember, like I said, the L completely changes in the two circumstances. The L in the T1 circumstance is going to be much larger. In the T2 circumstance, the L is much smaller. So you've made it a constant, and it's not a constant.
But you can, if you want. If it's really, you want to prove it to yourself that it really works. So that must mean the total time. So T, just by itself, well, that's T1 plus T2. But we can say, well, T1 is L over C minus V.
So again, he's using L as a consistent distance, and then trying to use the velocities that aren't the same. The C is a different velocity than the velocity of the thing moving, and he's strictly just kind of trying to add those when they're proportional to the distance. So they can't be done this way. This isn't integrating the time change. So the B is getting bigger as a percentage of the movement that the thing has. So the C part is moving, and at the same time it's moving, the L is expanding, and that's not in here.
And then plus T2 plus L C plus V. All right.
So there's no percentages, right? C plus V doesn't tell you that those are percentages. The light had to do most of the work in the lengthening circumstance. So when the dog's running away, the speed of light has to compensate for the dog going the wrong direction. And then when the dog's coming towards him, the speed of light is a smaller percentage of the equation, because the dog is consuming some of the distance now. So instead of making distance, the dog is consuming distance, and so the C component is actually going to be less than the dog component, in terms of there's going to be a larger percentage of dog component versus speed of light component, and in the other leg the speed of light component was the bigger component, and the dog running away was the smaller component. So the two are not proportional. They're symmetrically opposites, but their proportions, which one has the more work to do, changes. The percentages of the distance being controlled by the C or being controlled by the V change in the two circumstances. So you can't just say L over C plus V without acknowledging that C will have a more work to do in one circumstance, and V will do more work in the second circumstance.
And we're going to save that for later, because it's going to come in handy.
Yeah, there's really no point in saving it, in my opinion.
But notice that this is not some kind of a trick. You know, we're not dividing by 0. We're not doing anything like.
Well, you will be. So what's the point? You're going to start doing a bunch of Pythagorean theory kind of stuff and start doing area equations and volume equations and all kinds of other nonsense. So if you just left it this way, I mean, you could probably reclimate this. But again, there's still nothing in here talking about the fact that the length is increasing and decreasing.
That we're not canceling terms so that the wave equation cancels out and then you get a perfect wave or something.
Well,
we're
we'll
not
jump
doing
ahead, you know, because like I said, it does get quite convoluted. He takes numerous breaks.
But we have to derive it first.
To try to figure out what he's saying.
Hopefully you know the Pythagorean theorem, which is that
Oh, might as well listen to this.
well, if we have a right triangle and we have sides A and side B and we have side C, well, we can find the length of side C by doing this. We can go a squared plus a squared plus b squared equals c squared. Okay, now if we want to find C is equal to the square root of, and normally when you take the square root you would want to do plus and minus, but since we're dealing with lengths, they are always positive numbers, so alright, so that's the Pythagorean theorem, and we're going to use it.
Right, and what does that have to do with this? See, that's the point. It doesn't have anything to do with this, because this isn't about, you know, reaching some point in space where both things are heading for some point B. This is about this and going back, and all it is about when something's helping you consume the distance. So in one circumstance the red thing is consuming distance, in the other circumstance it's expanding the distance. Two fundamentally different things are happening, and of course the time it would take for one thing to happen than the other is going to be different. But the total time, it doesn't change. And he's not going to prove the total time has changed with any of this. And again, it's junk mathematics.
So
it's garbage.
let's see. We know that the distance traveled.
It's not relevant to
by the inner
what's actually happening.
Parameter. So okay. So really, what the picture is this is the beam splitter, and it's traveling v times t. So this is t1 again. And actually T1 equals T2, but you'll find that since it's perpendicular, we'll just double it. So we don't even have to do T1 and T2, we can just double it. You'll see what I mean in a minute.
No, I'm not going to see what you mean.
So the length that...
for all intensive purposes, the beam splitter just becomes the new emitter, so it just doesn't really matter. It becomes the new point A.
The light must travel, and you can say, well, how do we know that the light is traveling at a perpendicular angle? Not a perpendicular angle. How do we know that it's traveling at a hypotenuse? Why wouldn't it just bounce straight this way? And the answer is you don't really have to assume that. You could just assume. Well, I don't really want to get bogged down in all the bullshit, but
yeah, so He says it's all so simple, and yet there's bullshit to get bogged down in.
We'll just... Let's put it this way.
Yeah, let's put it this way. It's not so simple. Yeah. In my opinion, it's simple in the sense if you just analogize it to some other circumstance, like the dog or talking to somebody on a train, you can realize that, ah, yes, I see that it's just in one circumstance, the distance is getting smaller, in the other circumstance, the existence is getting larger, and that those two things are going to be proportionally opposite to each other. And so the total time is going to be exactly the same as if nothing was moving. The person sitting beside me is going to we're going to have the same length of conversation that the one across from me. There isn't going to be any change in the length of the conversation. Let me jump ahead a little bit. No, come on, YouTube. You're going to force me to reload a video just to jump ahead, are you? Oh, it's such a pile of crap, YouTube is. I mean, it's free and all that, but I mean, fuck. This is stupid. Reload a video. And it won't even do that.
No,
I can sort of understand. It's a cowboy video. Alright.
Key.
There we go.
Well, that's going to be, and this here we can simplify actually. I'm going to do that now.
Oh, cool.
Here's an interesting fact. Okay, if you have a squared minus b squared, this is equal to a plus b times a minus b, and we can even do an example. So let's say a equals 1, b equals 2, then we get 1 squared minus 2 squared is minus 3, right? Well, let's plug this in. Does this equal, and this is a question mark.
Well, you should put bigger numbers in just to be
1
sure.
1 plus 2 is 3. 1 minus 2 is negative 1. We get minus 3. It does indeed equal minus 3. Why is this true? Well, why is it the case that a squared minus b squared equals this? So let's get rid of all this crap. Well, this if we do FOIL, so this is a squared, first terms, outer terms, a negative times a positive is a negative, ab, inner, okay, it's b times a, plus b.
This is fun.
And then a positive times a negative is a negative, b squared. Well, these two terms here cancel because they're the opposites of each other. Minus ab plus ba. Okay. A times
Yep,
b
so
equals
drawing
b
around the
times
minus
a.
sign.
They're the same terms. You could just minus a number plus that same exact number is 0, right? Okay, this is a squared minus b squared. Alright.
Very exciting.
So, hopefully you were taking notes, or you can just pause the video, whatever. Or you can just not watch, or you can just not fucking pay attention. I don't give a shit.
Yeah, well, I'm just saying you're not really on the subject, so, whatever.
Alright, so this is equal to, I'm going to do the same thing. I'm going to multiply the top and bottom by, this is a neat little math trick. And, this is something physicists learned, this is something physicists do all the time. This is something physicists do. They know a lot of little tricks like this. Okay, this is something fine.
Yeah, so they ignore the fact that there is no L in the actual experiment. The L distance is never traveled by either length. Neither length will be L. So just ignore that truth and pretend you've compensated it with by saying somehow by altering the speed of light, by subtracting a velocity from it, that somehow you've accounted for which object is contributing to making the time take longer and which object is making it take less time. And that's only the V component. The C component is doing the same thing in both the forward leg and the backward leg. It's consuming the distance. The V component is the one in one length it's expanding the distance and the other length it's contracting the distance. And you can't do it this way.
And would have known when he was, probably 10 years old. But C plus V, well, let me make some more space. So actually I'm going to rewrite it again over here. This equals, and then L C minus V plus L C plus V. All right.
So you really couldn't get simpler, right?
By the same
so this
term,
is what I mean by math just being a gimmick. You've already got the equation as simple as you could need it to be. So just punch the numbers in. We have all the numbers, so punch the numbers in, you're done. So what other purpose is this gimmick than to break that simple equation? You've already got it reduced to as simple as you need it. We already have all of the values. We know what the speed of light is, we know what the velocity is of the object, and we know what the original distance is. So why are you taking the simple form of the equation and now complexifying it? Why don't you just do it? Oh, that's right, because you haven't broken it yet. You have to break it completely now.
C plus, oh, C plus V. Alright, if you multiply, this is like multiplying by 1. Okay, because the numerator and the denominator are equal. So that's the same as writing 1. But it just looks different. I'm going to do this over here.
I don't think you're doing it right. I mean, you're supposed to do the numerator on one side and the denominator on the other side. But whatever. Do whatever, however you want.
V. C minus V. All right, and remember, the order of operations, we should probably put little parentheses around here just to keep everything straight. All right. And I'm going to erase all this. Alright, what is this going to be? This is the numerator. It's going to be L times, well, I'm going to actually expand it. So we have C times L plus V times L. And actually, this down here, that's our little identity we had earlier. That's C squared minus V squared. Okay? Plus, we're going to do the same here, L times C, oh that's C times L, same thing, minus, so we have minus V times L, all of that divided by, oh look, same identity. Isn't that neat?
No.
And look at that, we have a common denominator.
Yeah, you just...
And what do we do when we have a common denominator?
Completely broke the equation.
Children.
Before there was something getting added and something getting subtracted.
We combine that to one fraction. C squared minus V squared. This is C times L plus V times L plus CL minus VL. Now, let's take a look at that. What can we do? What can we do? Oh, look at that. We can cancel terms. So this and this cancel. Isn't that great? So much.
And your C's cancel. And then you end up with L minus L plus L. C
well,
minus
looks kind of
L minus
doesn't
L.
It? We just have CL plus CL. That's like writing 1 plus 1. Why would you do that when you could just write 2? This is 2 times C times L Wow, look at that. What is that? What was that? What were we doing before? Oh, that's right. We were doing TL. Okay, so I'm going to write that here. TL. Okay. Oh, look at that. Look at this. This is different than this here. Look, the numerator's different. Look, that's one, and then this is the other one. They're fucking different. Okay. So, all right. So, we agree that they're different, right?
I agree that you complicated a simple equation.
Now, you might say, well,
and yeah, and turn it into garbage. But it doesn't matter. Let's just get to the fundamental argument. It is your belief that if I'm talking to somebody on a train, that my conversation takes longer if I'm talking in the direction we're moving than if I talk to the side. That's your argument. Effectively, that the two conversations don't happen exactly in the same total time, and that all that changes is the direction. When the distance is being expanded, it takes more time for the words to move, and when the distance is being contracted, it takes less time for the words to move, and that's all that changes. Yeah, that really should be enough. Oh, I'll play the psychotic laughter. That was really quite interesting. Let's see. Towards the end here, it goes into a whole psychotic laughter thing.
that's a smaller number. That means this whole thing is bigger than this.
So just notice the two L's again. So when we know that the lengths there is no consistent length. The L can't be the same. You can't use the same L. It's not a relevant constant, so to speak, because neither one of them will travel the same L. Yeah. Really helpful. He reminds me kind of like of those fist puppets, you know.
Yeah, that's bigger than this. Yeah.
So,
okay, so here we go.
I don't remember what I titled the videos, but this will be the third in the series. But obviously, it's just garbage. It's junk math. Just ignore the actual physical circumstance and the actual variables in the actual physical circumstance, and just play a game with numbers and pretend that you can somehow make something take longer than it actually took. So,
the conclusion. So we have that the length of travel. All right, so these are actually the same length relative. Oh yeah, they are. They're the same length legs. This is length L, right? This is also length L. The travel distance for the light, the little photons, they're not equal.
Okay. Right, but so your equation says they are. You said there's the same L in both sides of the equation. So obviously you're not accounting for the difference in the distance.
Okay, one of them travels farther than the other one, according to your your assumptions. So
yes, one travels less than the average distance, and one travels more than the average distance, and the two amounts are inverted, so it exactly equals to the same result. The normal conversation I have sideways will take just as much total time as the conversation in the direction I'm moving. It's just parts of the conversation will take place at different speeds, a different amount of time. The speeds won't change. The time it takes for the conversation will change because the word in one circumstance, the words are moving away, and in the other circumstance, they're moving towards. Duh.
Conclude that, yeah, your model does contradict the math, because you would expect to see a change in the fringe patterns. And the reason you would expect to see a change in the fringe pattern is because the distance travel is different.
So he still hasn't even acknowledged that just using one leg in the interferometer creates the pattern. So obviously it's not being created by any differences in any lengths. It's being changed because of the diffraction that's taking place at different angles because of the divergence of the light. So the divergence of the light changes where the rings are. Diffraction gradient is the thing causing the pattern, and you don't need a second length to compare it to get the pattern. So again, he's just not even acknowledging. He has no interest in facts. He just wishes to preach that crooked math. That's it. And so how can you have a conversation with somebody who just ignores the mechanical circumstance and what's actually mechanically happening? And that's what physics has become. Ignore the actual physical mechanical circumstance and just believe in your Heisenberg and believe in there is a real random in the universe. There's a random number generator that's real randomness. There's it's just bullshit. It's crap. So anyway, I don't know how else. I've given two perfectly good analogies, I think. That should be enough. You either understand that you can't change the amount of time by moving the whole experiment, or you don't. But you can't change it. What you'll lose going one way, you'll get back going the other. If they're 180-degree different opposite directions, you can't help but get back exactly what you lost. Alright, enough said.